Flying by ML. I'm Van Warren, and this is my dissertation proposal defense. I'm going to cover the use of convolutional neural networks for affine inversion. This work consists of 4 innovations. The first is that a change of view from VFR to IFR provides a large complexity reduction. The second innovation is that the trained test set can be generated from a single keyframe. The third innovation is functioning in the presence of 4 sources of noise. The fourth and final innovation is artificial interpolation using a CNN. First, we have some definitions. CNN stands for Convolutional Neural Network, ML for Machine Learning, RL for Reinforcement Learning. VFR stands for Visual Flight Rules, which govern fair weather flight. IFR stands for Instrument Flight Rules, which is almost all weather. AC stands for aircraft, and HW stands for hardware. Convolutional neural nets are fantastic and versatile creatures. I will explain how they work using MNIST, the hello world of CNNs. For further information, you may click these 3 links, which are down in the comments section below. Handwriting recognition using ML had its origins in the work of Jan LeCun and Corina Cortez of Google. They compared 64 CNN classifiers over the period from 1998 to 2008. If we take the 50 best classifiers, the mean test error is 1% and the standard deviation is 1%. In this work, I will extend CNNs to invert affine transformations, one example of which is rotation. To understand my extensions, it is helpful to understand how CNNs work in the first place. This page of code from a Python Jupyter notebook builds a 16-line MNIST CNN deep learning model. It runs in Google Colab, and you can quickly type it in and run it for free. There are 3 sections to this code. The first block of 3 lines is the import of essential TensorFlow libraries. The second is the loading and shaping of the data into tensor forms suitable for training. The third block is the definition of the model and the fit function call, which trains the model. The configuration arguments for the model are hyperparameters. I call them hyperams for short. Hyperams in ML are the result of a great deal of costly experimentation. Let's zoom into the details of the model. First, we declare a sequential model, which is a left-to-right ordering of the process pipeline carried out sequentially with backpropagation. Next, we add a 2D convolution layer that will create 32 feature maps representing idioms like loops and strokes in handwritten digits. The feature map is created using a 3x3 convolution operator acting on an input image of 28 by 28 pixels, 1 bit deep. Next, we add a pooling layer that reduces the number of pixels the neural net must consider. This speeds up the learn by a factor of 4. Next, we flatten the network. After that, we append a dense, fully connected layer of 100 neurons using a nonlinear activation called a rectified linear unit, or ReLU for short. It has a response curve that reminds me of a semiconductor diode. There are other activation functions we could use, like sigmoid or hyperbolic tangent, but ReLU works very well. Our activation function needs to be differentiable so that backpropagation of the neuron weights can be computed. Now we append a dense, fully connected layer. Then the output of 100 neurons is flattened into a 10 neuron final stage, which will use the softmax function to predict a digit. It is in this phase that my extension will occur. We then compile the model using the TensorFlow library operations of sparse category cross entropy with the Atom Adaptive Momentum Learning Optimizer and an accuracy metric so that we can track the learning curve. Finally, we train the model using a batch size of 1000 and 1 epoch for brevity. A quick sidebar on activation functions. The rectified linear unit can be implemented as a max function, which is both differentiable and very fast to execute. Despite its name, its job is to introduce nonlinearity into the machine learning process. Note the similarity to diode response curves, suggesting one could try using forward bias. The diode is the fundamental semiconductor device and appears here in a neural net. Why nonlinear activation functions? Because otherwise, many layers behave just like a single perceptron, and that's because the summation of linear functions would just produce another linear function. Key change for a sea change. When there's a change of paradigm, everyone starts at 0. To demonstrate this extension of CNNs, a relevant example is required. We will use one from the domain of general aviation, applicable to autopilots and self-flying aircraft. There are several technical revolutions affecting aviation worth considering in this context. The first is the machine learning revolution. The second is the web, edge, and cloud computing revolution. The third is the autonomous self-driving vehicle revolution. And the fourth is the drone revolution. Earlier this year, I proposed using a CNN for general aviation autopilot under VFR rules. This block diagram has two sections. The top section shows a video camera feeding a CNN, which outputs the current roll angle to a conventional PID, implementing Laplace transform control laws for a controller to keep the wings level. The bottom section shows a video camera feeding a pre-trained model, which outputs the current roll angle to a reinforcement learning program. The goal was to compare and contrast the performance of the conventional controllers to reinforcement learning controllers. My committee advised me to downscope my efforts, so I focused on the CNN. This led to some unexpected benefits. When I first conceived of using ML as an autopilot for roll control, I planned to place the video sensor on the exterior of the aircraft. My plan was to train the CNN to recognize all kinds of flight attitudes, terrain, lighting conditions, and weather. This was going to require collecting extensive training footage that was general enough to represent the combinations of all these circumstances. Imagine that you are flying by the side of a mountain, and the video sensor and ML combo think the incline of the mountain represents level ground. This is a problem, the solution to which illuminates an important robotic principle. Though simple to state in retrospect, it may be the most important step that was made. It turns out that by directly imaging the dial face of a gyroscopically driven instrument, three important problems were solved: a vast reduction in visual and computational complexity, a solution applicable to almost all-weather flight, and it was not necessary to tamper with expensive aircraft instrumentation. Specialized sensing devices reduced the ML workload and hardware requirements significantly. Amplifying this point further, robotic sensing imitates the biological. We could sense with our vision, but this would create a large and distracting cognitive overload. Instead, we determine our geometric attitude with a specialized sensor called the semicircular canals, one for each axis of roll, pitch, and yaw. We were made to fly. Now consider the six-pack of general aviation. The CNN sensing technique described here is applicable to all these standard instruments. We will start with roll axis sensing, which is provided by the bank indicator, part of a dual instrument called a turn and bank indicator. Even in modern automated cockpits, these basic instruments persist. Let's focus on the bank indicator component, which performs roll sensing in the turn and bank indicator. Some image processing is necessary to prepare the data for the CNN. We start with a 1036 by 1036 pixel RGB image of 3.2 megabytes. The first thing we do is crop and reduce the image to 600 by 600 pixels. This gives us a threefold reduction in the size of the image. Next, the contrast of the image is enhanced. Now the turn coordinator is clipped out, leaving just the bank indicator. Now we have an important decision to make. Should our robot see in color, grayscale, or black and white? Grayscale was chosen since the image edges alias as they rotate. Grayscale and bicubic sampling, preserving edge pixel values, improve the visual acuity of the CNN. Then we crop further to make the glyph of the instrument symmetric. A problem arises. As the clipped glyph rotates, part of the wing is missing. The solution is that we rotate before the previous clip when building the train and test set. The second innovation is that the train and test sets can be generated by the forward affine transformation of a single keyframe. One thing we notice when doing this, image processing, is that CNNs have incredible visual acuity. In the absence of noise, which we will add in a moment, the CNN tolerates an image reduction of a factor of 22. That is a 22-fold reduction in the amount of information that the CNN must process. So it can run 22 times faster and requires 22-fold fewer neurons in each one of the deep layers. Here is the standard k-fold cross-validation during training that shows the loss and accuracy function as well as the area of the receiver operating characteristic. An interesting statistical device that dates back to the invention of radar in World War II, but I digress. Functioning in the presence of noise. The next innovation is to make this work in real-world conditions that include four kinds of noise. The first kind of noise is sensor noise, such as would occur in the CCD of the video camera. The next kind of noise is variations in lighting that would occur in the cockpit at different sun angles. The next kind of noise we examine is camera position, and it's a fine operation involving translation. And the next source of noise is the camera zoom setting, which represents a scaling affine transformation. The next innovation is that we can do artificial interpolation with a CNN to invert the affine transformation that indicates the aircraft's roll angle. This is the most mathematically interesting innovation for me personally, and probably the one with the broadest applicability. It is called artificial because we interpolate categories of related objects to produce a numerical rather than categorical result. 4x4 matrix multiplies can rotate, scale, translate, skew, and apply perspective to geometric points in 3-space and to pixels and images. They are the bread and butter of modern 3D computer graphic hardware and software. Entire companies have been built around making these operations fast, starting with Silicon Graphics and continuing with NVIDIA. The CNN is adapted to recover the roll angle using the entire prediction vector. This inverts the usual process of affine transformation, analogous to the kernel trick in support vector machines. The kernel trick of support vector machines is to convert the dot product of the support vectors to the dot product of the mapping function. We usually think of CNNs as giving categorical results: car, truck, bicycle, or horse, zebra, dog, or cat. The CNN backend can be rewired to invert the affine transformation of rotation. We also use it to invert scaling and translation when noise is introduced. Artificial interpolation with a CNN. Here you see the previous method of choosing the maximum of the prediction vector to give the categorical bank angle. But in this case, we can take the dot product of the bank angle with the decision vector so that all the pieces contribute. Here you can see the hot spot in the prediction vector and the corresponding angles that will be included in the calculation. So in effect, we're gathering up all the inferred angle fragments and summing them up. Next steps. The remaining 5 slides enumerate next steps in completing the dissertation. The next step is to optimize the 16 hyperams. With 16 bounded cases and a midpoint, there are 43 million possible runs just to characterize the space. Thus, grid search is not feasible. A deep dive is currently underway using Jason Brownlee's optimization opus as a starting point, with another innovation in the works. The remaining 5 slides enumerate next steps in completing the dissertation. Using Python Jupyter notebooks and Google Colab GPUs in the cloud is a paradigm shift in software development. Many lessons have been learned, but the remaining struggle is how to decompose large problems into manageable pieces while retaining good visibility into the software details. This slide shows the tension between having one monolithic notebook and several smaller notebooks to work the problem. Here we see the statistics for an MNIST run side by side with a roll indicator run. This duality has been maintained for safety and verifiability reasons. The most important time saver is splitting the test train image generation from the inferencing task. Image generation currently takes more time than training, but it only needs to be done once. This slide shows the size of 20 code versions developed during prototype. At first the size increases, then it decreases as function libraries are factored out to external files. Version P has 1,232 lines of code, a significant departure from the 18-line example given above. This is a lot, given how terse and expressive Python is. This work required 189 references and multiple consultations. Every one of the aviation, technical, and development references were essential in constructing this proposal and software. The references accumulated during this work would make an interesting ML/Python tutorial on its own. So that's the end. Thanks for watching, and please click like in the link below.